Welcome everyone. We're going to go through some chain rule examples today. Our objectives for this video are to use the chain rule to find some derivatives. We're going to do a couple of harder problems near the end, so we're also going to try to make sense of the structure of those hard problems so that we can figure out what rules we need to use when we take some more of the complex derivatives. And the third thing is we're going to find the equation of a tangent line and use chain rule in that process. So what is the chain rule? So hopefully you're watching this with already an understanding of what the chain rule is, but the chain rule is the derivative of a composition function, so like an f of g of x is equal to the derivative of the outside, so the derivative of the f function in this case, keeping the inside the same, times the derivative of the inside function. So this notation is important. I'm going to try to point it out here and there when I can. So let's go ahead and get started. So the first thing that we're going to see is using the chain rule with the power rule. So if you remember the power rule, that is when you have a power function, you bring the power down and multiply that by the coefficient, and then you take one away from the power. We're going to do the same thing here. So first thing I'm going to do before I do anything is I'm going to rewrite this because it's written in a very ugly way. It's not written in a way that's going to help us use any of our derivative rules. So we know with exponents that if we have something raised to the power in a denominator of a fraction, that's the same thing as a negative power. So this is 2x to the third plus 1 to the negative 2 power. So it might help to list out what you see. I like making a list. It helps me sometimes. So the list of functions from outside to inside. The outsidemost function is you have something raised to this negative 2 power. And inside that you have 2x cubed plus 1. So the derivative of something raised to the negative 2 power would be negative 2 times whatever that is to the negative 3 power, right? And the derivative of this polynomial right here would be 6x squared. So this is the derivative of the outside function, and what we're going to do is when we take that derivative, we're going to have that negative 2. We're going to keep the inside the same, so this 2x cubed plus 1, and then that will be to the negative 3 power. And we're going to multiply that by the derivative of the inside, which we have found to be 6x squared. So that is technically done. It's not written properly, but that is the derivative. To write it properly, let's multiply the coefficient with this derivative here, so we can have negative 12x squared. And then we can bring this negative power back down to the denominator, so that would be 2x cubed plus 1 to the third power. And that is the derivative. That is f prime of x. All right, so the chain rule is kind of following along what's outside, what's inside, identifying those features, and then taking the derivative of each of those separately. Remembering when you take the derivative of the outside, you're keeping the inside the same. So let's look at these two here. These two here are very different, but they look really similar. So if I look at this one and I identify what's going on, I have sine cubed x. Well, from pre-calc, or maybe your Algebra 2 class, you'll remember that this can be rewritten as sine of x cubed. That's just a fancier way to write it, so you don't have to add those parentheses all the time. So if we were to list out the functions here, we have something cubed, and then we have sine of x. The derivative of something cubed is 3 times something squared. Derivative of sine of x is cosine of x. So the derivative of this is going to be 3 times, keeping the inside the same, would be that sine x, and then we'd have that squared, times the derivative of the inside, which would be this lovely cosine. We can clean this up a little bit to make it look a little bit nicer. So we can have that 3. We can make this look pretty again by doing the sine squared x, and then we can have that cosine x. And that would be the final simplified derivative. This one here looks very similar, but look at the structure. It's not the sine itself being cubed, it's the x. So this will trip up a lot of people, and it trips up a lot of my students. So when we make this list, what's on the outside this time is that sine of something, and the inside of that is the x cubed. If you wanted to, you could make this, if you wanted to like really cement what's going on, this would be sine of x cubed. And that's where we're getting this inside, the outside and the inside from. Derivative of sine is cosine of something, and the derivative of x cubed is 3x squared. So the derivative of this is going to be cosine, keeping the inside the same, times the derivative of the inside, which is at 3x squared. We can clean that up a little bit. We can bring the power function out in front so it looks a little bit prettier, and we can have 3x squared cosine x cubed, and that is what h prime of x is equal to. So hopefully you see it's not that bad. It's derivative of the outside, keeping the inside the same, times the derivative of the inside. We're just following that process. And if it helps to identify the structure, I do recommend making a list, especially if you're new to it and you're having trouble. If you're able to identify the inside, the outside without it, by all means, skip that step. So let's find a tangent line using this. So something your calculus teacher should be going over consistently is why we take derivatives. What is a derivative? Why is it useful? Its application. And one of the biggest things is tangent lines. So remembering that the derivative of a function at a certain point is the slope of the tangent line at that point. And tangent lines can be rewritten, or can be written as y minus y1 equals m times x minus x1. So they gave us the x. The x1 is equal to 2.5. We need to find the y1 and the m. We can find the y1 by just plugging in this 2.5 into the function. So let's do that over here. So f of 2.5 is equal to 3 over the square root of 9 minus 2 times 2.5. Now, I don't know how you are or how your math teacher is. I get to be a little lazy when it comes to this stuff. I'm not going to rewrite every single little step. I know that I got to clean up the inside of this square root because right now it's pretty ugly. So 2 times 2.5 is 5. So inside the square root, we have 9 minus 5 inside that square root. 9 minus 5 is 4, so we have the square root of 4 in there. So this is equal to 3 over the square root of 4, which is 2. And that, again, is our y1 when it comes to this equation. So we got 2 of the 3 pieces. Last thing we need is the slope, and we need the derivative for that. So before we take the derivative, this looks awful. Let's make it a little bit easier to use with some of our rules, because I personally don't want to use quotient rule on it. I'd rather use the power rule. So if I want to clean this up, I could have 3 times the square root. Well, let me write the inside first. The square root is the same thing as the 1/2 power. And it being in the denominator, we've already talked about, makes it negative. So this is to the negative 1/2 power. And that again is what f of x is equal to. We're interested what f prime of x is, what the derivative is, right? So what's inside, what's outside? I'm going to make my list over here. Outside we have 3 times something to the negative 1/2 power. And inside we have 9 minus 2x. The derivative of 3 times something to the negative 1/2 power, well, we bring the power down, so that'd be negative 3 halves times what, well, times the inside, and then we take 1 away from the power. So negative 1/3, negative 1/2 minus 1 is negative 3 halves. Again, a common mistake. They'll say that it's 1/2, you take away 1 from 1/2, it's a negative 1/2, and they'll forget that step. So that's a very common mistake. Do your best to try to play around that. Here's another one. The derivative of 9 minus 2x is negative 2. Don't forget the minus in front of the 2x would make the derivative negative. So this is the structure. Let's rewrite it. So we have f prime of x is equal to, we have this negative 3 halves, keeping the inside the same, so we have this 9 minus 2x, and then we have to the power of negative 3 halves times a negative 2. Now, you can just plug in the value here. I'm going to clean it up a little bit, mainly because I see that this is a fraction that I can easily get rid of, so I'm going to. So f prime of x is equal to negative 3 halves times negative 2 is a positive 3. And that's all I'm going to do. I'm not going to rewrite this in its proper notation, mainly because in the end it's not really going to matter much anyway. At least not right now. We'll save ourselves some writing by avoiding that right now. So what we're going to do is we're going to take this x value and we are going to plug it into our derivative. So we want f prime of 2.5. So that is 3 times. We've already said that 9 minus 2 times 2.5 is 4. So let's just rewrite that as 4. We've already done that work. Let's not do it again. Now this, we got to clean up a little bit. I don't know about you, but I don't know that off the top of my head, so I'm going to make it look a little bit prettier, a little bit nicer, and see how that turns out. So we get this 3 times. The negative's going to bring it to the denominator over 1. And then we have 4 to the 3 halves. The half power is a square root. The square root of 4 is 2. So this is 3 times 1 over 2 to the third. 2 to the third is 8. Multiply fractions straight across. So f prime of 2.5 is equal to 3/8. Now, I don't know if you're a fraction person or a decimal person. Since we got this 8 here, I got half here, like, I'm going to change this to 5 halves just to make my life easier. I like to be all one way or all another. So our tangent line will end up being y minus, we said our y1 was 3 halves, equals our slope, which is this 3/8 times x minus our x that was given to us, which is 5/2. If you put a 2.5 and your teacher takes off for it, I'm sorry, that would be awful. I wouldn't, personally. But that is the equation of a tangent line, and we use the chain rule in finding that. So it's always important to remember why we're doing this, and a very easy question that will come up often, especially if your teacher is good about reminding you about it, is derivatives and tangent lines go hand in hand. Things my students currently struggle with, and that is when we have the chain rule and product rule together. What happens, what goes first, what takes precedence? These are the hard problems I was talking about. And here are the two different versions you'll see, at least in terms of like structure. So we have something like this, and then something like this. And if you notice, this one here has multiplication being the most prominent part of the structure taking place. You have a function times a function. Here, you have composition of functions taking precedence. You have the natural log of two functions being multiplied. So when it comes to that determines what you do first. Whatever the big thing happening is takes precedence. So I'm going to move, there we are. I am going to move this out of the way for now. We'll come back to it. But for now, I want to tackle this question here. Now, I do product rule a little differently, and if you're one of my students, you already know, I like to use what I was taught as the fish method. So I'm going to write it out. If it doesn't make any sense to you, I'm so sorry. Just do what you're used to, and then check your answer against mine at the end. So the first function I see is 2x plus 1 to the 5th. Second function I see is 3x minus 2 to the 7th. So again, multiplication is the big structure taking place, so the product rule is the first rule we're going to use. Now the derivative of this, I'm going to need the chain rule for. And I'm not going to make the list for these because these are relatively simple. But when you see ones that are more complex, or if you're struggling, again, make the list. It's all about what works for you. So the derivative of this would be 5, keeping the inside the same, to the 4th, times the derivative of the inside, which would be 2. And I'm going to leave it like that for now. We can clean it up a little bit later. Derivative of this one would be 7. And then we would have the inside staying the same, to the 6th, times the derivative of the inside, which would be 3. And then we are going to, as my kids would say it, we're going to plus fish it. So we have this part here, which is 5 times, well, we can make that look a little prettier. 5 times 2x plus 1 to the 4th times 2 times this function right here, which is 3x minus 2 to the 7th plus, we have this 2x plus 1 to the 5th times 7, 3x minus 2 to the 6th times 3. A lot of stuff, right? And I could have saved myself a little bit by cleaning it up earlier, but for now, it's a little ugly, and that's okay, because I really want you to see the structure, especially if you're not used to the fish method. that this is f prime, and this is g. This is f, and then what is all of this, I'm sorry, is g prime. So it's still the method you know, it's just a way of organizing it that I teach my kiddos. All right, we clean this up a little bit by multiplying the coefficients. So we have 10, and then 2x plus 1 to the 4th, 3x minus 2 to the 7th, plus 21 times 2x plus 1 to the 5th, 3x minus 2 to the 6th. Now, if you're one of my kiddos, or maybe your calculus teacher's the same way, that is calculus. That is a correct answer. That is the correct answer or equivalent to it. Now, depending on how strict your teacher is, they might ask you to go a little bit further with this. We can actually clean it up a little bit more. And we can do that by factoring out the greatest common factors from our two terms, because we do have two terms. We have this right here, and then we have this right here. So we can factor out the greatest common thing, and we can clean it up a little bit. So let's do it just for kicks and giggles. They both have 2x plus 1s, and they both have 4 of them in common. So let's factor that out. So 2x plus 1 to the 4th. And they also have that 3x minus 2 in common. And they have 6 of those in common. What does that leave us with? Well, it leaves us with 10. We took 4 of those out, so that reduces to 1. And we're left with one of these. So 3x minus 2 plus the 21 would stay. We took out 4. We factored out 4 of the 2x plus 1s, so we're still left with one of those. And we took out all 6 of those, so there wouldn't be any left in here. We can clean this up a little bit as well, so we can distribute and then combine. So we would have 30x minus 20 plus 42x plus 21, and that'll condense down as well. So we have, as a final answer, 2x plus 1 to the 4th times 3x, ooh, looks a little ugly, 3x minus 2 to the 6th times, and if we add the like terms, we should end up with 72x plus 1. And that is f prime of x. Sorry, it looks a little ugly at the end. But that is completely simplified. So depending on your teacher, depends on what they'd accept. My kiddos, I would accept this. But again, that kind of depends on your teacher. Here we have h of x equals the natural log of x sine x. So here, if we look at the structure of this problem, it is function composition that takes precedence. We clearly have a function of some sort inside of another function. So chain rule is going to take precedence here, and that's how we're going to start. So I'm going to start by making a nice little list here of what our functions are. We have this natural log of something, and then we have this x sine x here. The derivative of the natural log of something is 1 over that something. The derivative of x sine x, a common misconception my kiddos have is that they will say it's cosine because they will think the derivative of x is 1, derivative of sine is cosine, 1 times cosine is cosine. But they forget that this is actually product rule. It's very sneaky sometimes, and so we have to use the actual rule. My kiddos like to set up fishes, so that's what we're going to do. We have x for one function, and we have sine of x for the other. The derivative of x is 1. The derivative of sine x is cosine x. And we'll set up our fish. 1 times sine x is sine x plus x times cosine x. So that would be x cosine x. So now we have an idea of what's going on. We have the derivative of the outside, we have the derivative of the inside. We can set up what chain rule is. So chain rule is the derivative of the outside, keeping the inside the same, so this inside of x sine x, and we're going to multiply that by the derivative of the inside, so this string of sine x plus x cosine x. Now, technically this is the derivative, but it's not very pretty. So we can make it a little prettier by distributing. If we distribute the 1 over x sine x to the sine x here, the signs would cancel, and that would leave you with 1 over x. And if we distribute the x sine x to this x cosine x, this 1 over x sine x to x cosine x, the x's would cancel, and we would be left with cosine over sine. And cosine over sine is cotangent. So our final simplified answer for the derivative would be 1 over x plus the cotangent of x. Again, this is correct, but most teachers want you to simplify, and this would be simplified. The last example I have for us is this double chain rule, a function within a function within a function. So with chain rule, since you're taking the derivative of the outside, keeping the inside the same, and then multiplying by the derivative of the inside, if that inside function is a composition function in itself, use the chain rule again. So we get these wonderful chain links of derivatives, and this is what the rule would end up looking like. So if we had f of g of h of x, and we wanted the derivative of that, we would take the derivative of the outside, which is the f function. We would want f prime of g of h of x, because we'd want the inside of that to stay the same. Then we'd multiply that by the derivative of the inside, so the derivative of the g function, keep the inside of that function the same, so that each function stays untouched, times the derivative of the h function. So this is what the rule ends up looking like. I like to still make a list, especially with more complicated ones, that way I can still see what the structure is. For a problem like this, again, when we have this sine 4, we have sine to some power, it's easy to rewrite that so we can see the structure as sine of 7x to the third power plus 1, and all of that to the fourth power. Now it's clearer to see which functions are inside and which functions are outside, but again, if you're having trouble, or you just like doing it, we can make a list. So the outermost function is something to the fourth power. Inside of that is this sine function, and inside of that is this 7x cubed plus 1. The derivative of something to the fourth power is 4 times that something to the third power. The derivative of sine is cosine. And the derivative of 7x cubed plus 1 would be 21x squared. So let's set that up. Let's set up the chain rule here. So we're going to have f prime of x is equal to, well, the first derivative would be 4 times, keeping the inside the same, so this is sine of 7x cubed plus 1 to the third power times the derivative of the inside, which would be cosine. Keep the inside of that the same, so this 7x cubed plus 1 times the derivative of that, which would be this 21x squared. And we can clean that up by rewriting this nicely and then multiplying the coefficient by the power function. 2 times 21 is 84 x squared. We can have sine cubed of 7x cubed plus 1 times cosine of 7x cubed plus 1. Hopefully, after we've gone through these couple of examples together, that you feel a little bit more comfortable and confident with the chain rule. Hopefully you feel like you can use the chain rule to find derivatives, that you can identify the structure of a function to find more complicated derivatives, like when we did the product rule within chain rule, or the double chain rule, so on and so forth. And hopefully you feel like you can find the equations of tangent lines with derivatives that involve using the chain rule. Hopefully you're feeling a little bit better about everything, and I'll see you all in the next video.